Now let us talk about octahedron. Octahedron is also an old friend. Whenever you talk about metal complexes, more often than not you talk about octahedral complexes, right? And I think in the previous class we talked about the balloon experiment. Did you or did you not? Right? So you have 6 balloons of equal size, right? Tie them in twos and then try to tie them together, you will get an octahedron. Okay, this is octahedron. Octahedron is another Platonic solid because you have more than one principal axis of symmetry. Right? Let us see what we have. What next? What is the principal axis of symmetry? An octahedron is basically made up of the 3 axes once again, x, y, z. Okay. What is the principal axis of symmetry? So principal axis of symmetry is C4. How many such axes are there? 3. X, Y, Z. How many operations? C4. The C4 square is C2. So we classify it separately. And then C4 cube is another operation. Right? This is your axis. And there are 3 such. These are the operations 6C4. And you can also get 3 C2s arising out of there, where each C2 is basically C4 square. Right? Any other axis? C3. Where is C3? And this is where you see it better if you tilt the octahedron a little bit. So you see A, B, C form the apex of a triangle, and then A, B, C form the apex of another triangle which is pointing the other way. Okay. So together, if you look from the top, they form something like a David star, Star of David. Okay. Now if you think of this axis here, is it not a C3 axis? Is it not a C3 axis? Got it? Is it clear? Unfortunately, I don't have a, but I can still show you. These are the 3 axes. Okay, at least half of a tetrahedron, half of an octahedron. Look at it like this. Do you see C3? I can rotate like this, right? So that is C3. And here you see the whole picture because you see not only the top but also the bottom. Okay, C3 axis. How many C3 axes will be there? 4? 4, 3? Huh? Eight C3 operations. 4 C3 axis is right. So it's basically 3-dimensional space, right? You can divide the top part of it into 4 quadrants and divide the bottom part of it into 4 quadrants, right? And where is the C3 axis? C3 axis goes through the center and between 2 diagonally opposite quadrants. How many such sets will be there? Right? And each C3 you can have C3 and C3 square. So 8 C3 operations. Okay, next one is C2. We already have one kind of C2, right, which arises out of operation of C4 twice in succession. We have another kind of C2, isn't it? Which is 45 degrees with respect to this, which bisects the bond angle. So second kind of C2. This is also C2, but another kind of C2, different class. How many such C2s will be there? 3? 3 or 6? Huh? How do you figure out it's 3 or 6? In each plane you are going to have 2. And what kind of plane is this? The way I have drawn it, let us say this is x-axis, that is y-axis. Then I have drawn this C2 axis in the xy plane. How many such planes can you think of? x, y, y, z, z, x, right? Each of these planes will have 2 C2 axes, so 6, all right? 6 C2 is also there. Okay? Anything else? Yes. Don't forget I, poor I. I is also there, right? Then yes, S4 will be there, S6 will be there, and now come to the planes. Can you read that it's sigma h? That comma has come too close. Before I send it to you, I'll move the comma aside. You see the sigma h? Do you agree it's sigma h? Let's say xy plane. XY plane is sigma h. Do you agree with that? What is sigma h? Horizontal plane. What is the meaning of horizontal plane? The principal axis should be perpendicular to the plane. That's what I am more comfortable with. Right? So principal axis, so what is the principal axis then? If it is xy plane, z axis, if you take z axis to be principal axis, then xy plane is a horizontal plane. If you take y axis to be the principal axis, and you can, right? All three are principal axis. So if you take y axis to be principal axis, then zx plane will be the horizontal plane. If you take x axis to be principal axis, then yz will be the horizontal plane. So 3 horizontal planes. Okay, very high symmetry. Multiple principal axis, multiple horizontal plane. So that is why these are special kinds of structures. But don't forget, we are saying that octahedron has very high degree of symmetry. Even octahedron has very low symmetry compared to a perfect sphere. Think of a sphere. How many symmetry operations, how many symmetry elements will be there in a sphere? Infinite. Infinite number of Cn of any kind. C2, C3, C4, C5, C6, C8, C923, infinite number of each, isn't it? So sphere is a perfectly symmetric shape. So even though octahedron has very high symmetry, it is nothing compared to sphere. Okay, that's why in sphere everything is degenerate. Okay, anything else? Sigma d, where is sigma d? I have not drawn it. Sigma d will be along these C2, right? And what do these sigma d's do? They bisect the angle between this C2 and this C2. That is why they are called sigma d's. Are you convinced that these are sigma d's? To be sigma d, first of all, it has to contain the principal axis. So this thing that we have here, okay, does it contain a principal axis? Yes. It does. And it also bisects the angle between two C2 axes. That is why they are sigma d's. So see, so many symmetry operations are there. If you add them, what will you get? You will get 48, I think. That is the order. Order means total number of symmetry operations. So this is called octahedron OH. Okay. Now, before going there, maybe take, after all these difficult examples, take an easy example. Ethylene. Ethylene, does it look like ethylene? Huh? Tell me what are there. E, then what is the principal axis? C2. Now I can see one C2 here and another C2 here. Which one will you take as principal axis? Containing more carbon atoms, more atoms, right? So this is principal axis. So this is one C2. You have one C2 here. Is there any other C2? So if the principal axis is Cn, and if you have at least one C2 perpendicular to it, then it implies that the total number of C2 axes perpendicular to Cn is always n. So you should always look for n minus 1 more C2s. Okay. So this is one, this is one, this is one. 3 C2s. Once again x, y, z. Okay. Horizontal plane of symmetry, is it there? It is there. So now you don't even have to look any further, isn't it? Right? Which point group is it? D2H. Don't forget the perpendicular C2s. Alright? Now, another very typical example. What is this? Ethylene diamine. This ethylene diamine, cobalt 3. Okay. What is the structure? I am not drawing cobalt. Okay, it's in the middle. What does ethylene diamine look like? Ethylene diamine, isn't it? So, what I could do is I could just draw like this 1, 2, 3. They look like 3 blades of a rotor. Okay, this is a very typical molecule that people like to work out the symmetry point group of. This ethylene diamine cobalt 3. Can you tell me what will be the symmetry point group? See, the basic structure, the basic disposition is octahedral, right? So, it makes sense to start thinking in the lines of what is there in an octahedron. Of course, many of them will not be there. You will have much fewer number of symmetry elements there. But it makes sense to start thinking what is there in octahedron, start from there. I will start with 1, E. It's definitely there. What is the next? What is the principal axis of symmetry of octahedron? Principal axis is C4. Don't forget C4. Huh? C3 is vice principal axis. C4 is principal axis. Do you think C4 will survive here? No way. Very obvious. Okay? C3 and C2 may or may not survive. That we have to work out. I'll give you the easier task first. Look for C2. Perhaps the easiest way of doing it is write like this. Give them names. A, B, C, D. This one is E. I'll just write it a little far away. F. Okay. Now try to do something. Where were the C2s? Remember? Two kinds of C2 basically, right? How many C2s that we'll see later. But there are two kinds of C2s. What are the two kinds of C2s? Yeah, along the C4 axis, and the other was in between the C4 axis. Along C4 axis would be EC. You think that C2 survives? No. So the only C2 that might survive is in between, like this. This one. So do you think this is C2? Let us see. Let us do this operation and see what happens. Forget about the connectivities to start with. Okay? Just perform the C2 operation. See which letter goes where. If you perform C2, E and C will be interchanged, isn't it?
Yes.
Right? So I will write E here, I will write C here. Then
B and F.
I made a mistake. I made a mistake. Let me write it here. Actually, D and E get interchanged, isn't it? D and E get interchanged. So D comes here, E goes here. B and F definitely get interchanged. Are you okay with that? B and F get interchanged? Sure? So C comes here and A goes there. Is that right? Now, what were the rings? BC was a ring, right? BC was a ring, right? Let me join BC. Then E and D and A and F. Now tell me, allowing for my pure artistic skills, have you not got an indistinguishable molecule? You have, right? Right? How many such C2s will be there? 3. Okay. Now can you try the C3s? Don't forget where the C3s are. What is the easiest way of working with C3s? By drawing that Star of David. Okay, these are not bonds, they are just guides to the eye, okay? Now, if you look from the top, from this corner, what do you have? I have D, if I look from the top, BCD, then I have D on the left, B on the top and C on my right. Is that okay? D on the left, B on the top, C on my right. You understand from which angle I am looking? Huh? Do you understand which angle I am looking from? Okay. So, think of the triangle BCD. You see BCD? So BCD, think of BCD as an upward pointing triangle. Now do you understand from which direction I am looking? Yes. Huh? BCD is the upward pointing triangle and then EAF is the downward pointing triangle. Is that so? Right? So if I draw that in the Star of David form, what will it look like? D, B, C. And then, what is the downward triangle? E on the left, A on the right, F at bottom, right? What are the rings? BC, ED and AF. Right? BC, ED, AF, BC, ED, AF. These are the actual rings. Let me draw the rings. BC, AF. We have drawn it, it's a little difficult. Anyway, and DE is easy to draw. Okay. Now let me see, let me perform this C3 operation and let's see if it will survive. B, C, D, E, A, F. Is that right? I've turned clockwise. Alright, forget about the rings while turning. Just look at the letters. Have I turned correctly? Just considering letters, nothing else. Now join what? D and E. You don't need to look any further. This is not a symmetry operation. So what do we have to do? How many C3s were there? Huh? 8 C3 operations, so 4 C3 axes. So now similarly you have to try out all the 4 C3 axes. This C3 hasn't survived, that's for sure. What about the other C3s? That is what you have to work out. Okay, I'll leave that to you. If you cannot do it, we'll tackle it in the next class, okay? Because it's just brute force. You have to look at all possible C3 axes. I'll give you the answer. One C3 axis does survive. One C3 axis survives. So you have C3 and you have 3 C2s. So point group is D3. This is a very celebrated example of D3 point group. Okay, nothing else is there. D3. So try to find that C3 axis by yourself. Now let's come back to this. Now, the previous discussion was by and large from Cotton's book. This discussion is a little better in Carter's book. So I'd like to draw your attention to something that we are going to use later extensively, and that is group subgroup relationship. And actually we have already discussed that today. We said, right, that you start with a tetrahedron and you stretch it, you get D2D. So D2D is like a subgroup of tetrahedron. Okay? Similarly, what we have seen is this D3 can arise out of octahedron. So let's see what happens when we start with an octahedron. Oops. Have I brought the book? What I planned is, this is an octahedral molecule, Ma6. Okay. Do you see Ma6? Huh? Now, let us think of two pathways. Let us say we substitute two of the A's by B's. Whatever A and B might be, that doesn't matter. A is a ligand of one kind, B is a ligand of another kind. Okay? First, let us consider this. I have done a substitution like this. Actually, here what we have done is we have substituted by 3 B's. So it's become Ma3B3. What is the point group? Ma3B3. Because the answer is written beside it. Thankfully, it is very small in the projection. It is C3V. It is almost like two ammonia molecules back to back. It's just that the bond angles are not correct for ammonia, isn't it? So see, C3V is a subgroup of OH. You can go from OH to C3V by chemical substitution. And this is actually very important because all the time what we want to know is what happens to the energetics or spectrum, etc., when we do a chemical substitution. Okay? And this is what is going to provide us with that answer. And if you take another route, start with Ma6, right, and perform this kind of a substitution, axial substitution, right? Two A groups opposite to each other have been substituted by B. What is the point group? I am just hoping that I was fast enough. What is the point group? What is the principal axis? C4. No surprise, principal axis was C4 even for octahedron. What is the difference here? There are 3 C4s. Here you have only 1 C4. 1 C4. That BMB is the only 1 C4. C4, no, you are turning with respect to that. Okay, only 1 C4 survives. The other 2 C4s are gone. Okay. So if there is a single principal axis, what is the next thing that we look for? Do you have a horizontal plane? Do you have a horizontal plane here? Yes. This A4 plane is a horizontal plane. And do you have C2 axis perpendicular to the principal axis? You do. How many? 4? 4. So no need to look any further. You also have diagonal plane. You also have inversion symmetry, right? But all that is not relevant as far as nomenclature is concerned. You just call it D4H. So D4H is a subgroup of octahedral. Now, if you do a further substitution, instead of two B's, you have a BC. Then what happens? C4 survives. Horizontal plane is gone. So what is the point group? C4? D4? C4V. The perpendicular C2 axes are also gone, but you have horizontal planes, vertical planes. How many vertical planes? 4 or 2? Sure? 4 or 2? One kind or two kinds? What are the kinds? Through bond and between bond, isn't it? So two kinds of sigma V. All right. So this is your C4V. So C4V then is a subgroup of tetrahedron, octahedron, OH group, as well as your D4H group. Okay. This is something that sounds very simple, but you will see this will help us simplify our calculations to a very great extent when we actually start using symmetry to talk about molecular properties. Okay. What is this? Further substitution, right? Two axial substitutions and then two other substitutions. What is this then? Is this C1? C1 kind of molecule? Now can you? M A2 B2 C2. What is it? Sure? Huh? C2V? This is like three water molecules with not incorrect bond angle back to back. C2V. So C2V is also a subgroup of your C4V, D4H and OH. Right? So remember this group subgroup relationship. This is going to come handy in later times. What I'll do is, before I give you the slides, I just put it in here so that you don't need this hand drawn thing. Okay. Now your time is almost over.